recovery technologies going back to 2002, and he began research on controlled struvite vassalization at the University of Wisconsin-Madison. Since then, he has worked on numerous projects related to the nutrient upcycling and its leading development of phosphorus and nitrogen recovery technologies at NRU and CNP.
Thank you. Thank you. Thanks for attending my talk. So I'm going to talk about phosphorus recovery and the utility of the future. I'll give just a brief overview of just phosphorus in wastewater, and then I'll go into a Water Research Foundation project that we did last year on a technology that we're developing at NRU and CNP. And then I'll open it up for questions. So just to promote this more, we're changing wastewater to water resource recovery facilities. And brief overview of what we're recovering is clean water, carbon, and minerals. And what we're working on in our company is right now phosphorus and nitrogen. And for this talk, I'll focusing simply on phosphorus. So what are the drivers for a utility to do phosphorus recovery? This has become more of an issue in the past 10 years, and so we surveyed multiple utilities to see like what's happening around the country and why are people motivated to do this. And there's quite a gap between the different regions for why people would do phosphorus recovery. For example, in the Midwest, getting the phosphorus out of the biosolids is one of the most important factors, versus on the East Coast where they have, where a lot of utilities have ocean outfalls. The driver might be purely economic. So when we look at what are the drivers, it comes down to 5. Reduction of phosphorus load in the biosolids effluents, which gets recycled to the headworks. This is related to cycling phosphorus around, from after dewatering the biosolids. Struvite control, pre and post digestion. So some facilities might not necessarily need to recover the phosphorus, but they have an enormous struvite problem, and so getting the phosphorus out is a really big deal for them. The other thing is dewatering efficiency of the biosolids. We see an increase of 3 to 5% in total solids and about 30%, 25 to 30% reduction in polymer use when you remove the phosphorus from the biosolids. And then the fourth one is the nitrogen to phosphorus ratio in the biosolids, and this is a key thing for the Midwest where we're based, and that's really important because a lot of the soils around utilities are overloaded with phosphorus, and if you remove that phosphorus, you can apply more towards the nitrogen in the biosolids rather than the phosphorus in the biosolids. And then last but not least is that if you do phosphorus recovery, you recover a valuable fertilizer. And you could then, because you're concentrating that phosphorus in a fertilizer form, you can transport it basically anywhere because it's interchangeable with other phosphorus minerals in the market. So most of you probably know this already, but for those of you who don't, from the phosphorus that comes into utility, I would consider that 100% of the phosphorus here. About 10% of it goes into the primary sludge, 10% goes to the outlet, and about 80% is in the waste activated sludge. And so very easily you can see where the location is that the biggest kind of value for recovering phosphorus is typically in the waste activated sludge. And so what we focus on and what we're seeing more and more is more customized solutions for utilities based on where how their sludge process works. We focus on a solution for phosphorus recovery before the digesters, after the digesters. And more recently, we're seeing more possibilities to combine, like, for example, dewatered filtrate with a pre-digestion centrator filtrate, and which can work too. Or, as was mentioned in the presentation yesterday, in the case of a post-aerobic digester, you can also you have a very high rate of soluble phosphorus there. So one of the key factors for the forward flow of a wastewater treatment plant is sequestering that phosphorus into the solids. And then what we then try to do in terms of capturing a high rate of phosphorus is then to resolubilize that phosphorus out of the solids so that it can then be recovered. So I made this morning just kind of a very subjective kind of overview of like what's going on with phosphorus recovery and depending on where you're recovering it. And so I see basically 4 locations for where you can recover phosphorus. It's either pre-digestion, post-digestion, post-dewatering, and then more in Europe, there are some people doing ash phosphorus recovery. And there are pros and cons for each of those locations in terms of how much phosphorus you can recover, what the, like whether the sludge is digested or not will depend on like whether you can have a class A at that location, or you have to do more treatment to make sure that that you have low pathogens. Heavy metals is usually not an issue for the first 3 locations, but if you do ash recovery, heavy metals becomes a really big issue. In terms of minerals, typically in a utility you'll see either struvite or brushite or some other calcium phosphate mineral, and then from the ash it's more closely aligned with a typical fertilizer manufacturing, and there are more possibilities for phosphorus fertilizers from there. In terms of upcycling, all locations are pretty good at recovering a product except for post-digestion because it's very difficult to settle out a mineral from a 5% sludge. Then in terms of capital cost, probably the most expensive is the ash recovery process, and then the others are really dependent on the utility. So I'm going to kind of start focusing in on what we're specifically doing and the study that we're working on. And one of the key distinctions I'd like to make to start with is the difference between brushite and struvite. Brushite is a calcium phosphate mineral, meaning that it doesn't have you don't need ammonium in solution. So some utilities, especially for example after post-aerobic digestion where you have very low nitrogen, it's not ideal for making struvite. You can make brushite instead. It also forms under slightly acidic conditions versus struvite, which is under slightly alkaline conditions. So as I said earlier, one of the key factors for how much phosphorus you can recover from during digestion is how much of that phosphorus you can resolubilize into solution. And there are many ways to do this. One of the ways that we focus on is just a simple fermentation step. And in our case, we like a longer fermentation time, closer to 24 hours or a day and a half. Whether it's specifically a fermenter or an acid digester is not that important. It's really the residence time. And as you can see from the different steps here, you have the highest rate of soluble phosphorus when you get into the, an acid fermentation or acetogenic fermentation. And the reason for that is that it drives the pH down and it keeps the minerals within solution. Once you get into a thermophilic digester or mesophilic digester, pH naturally rises, and then that phosphorus precipitates with the calcium and magnesium. And so already, once you get further into the digestion process, you don't have as much phosphorus available to recover. and so the total phosphorus recovery will be lower. We've also, just to illustrate some of this, we've over the years collected samples from multiple facilities, and both that had WAS primary mixes or just WAS only fermentation, and we get anywhere from on the last line 36% total phosphorus solubility to around 90% total phosphorus solubility. And what's the key dependent factor here is how well the fermentation is occurring within that facility. And typically the facilities that have a WAS primary mix have better fermentation. So in terms of the two processes that we're developing for recovering that phosphorus, the first one is called Calprex, the other one is Airprex, and some of you, most people probably know Airprex by now because of Gerhardt, especially here. But in terms of Calprex, first step is the fermentation, then we do dewatering to get the solids out. Brushite, unlike struvite, doesn't form large crystals. It's between 2 and 500 micron particles, so you need the TSS out of solution. And then we have a centrate that we react with calcium hydroxide. We bring the pH from typically around 5.5 to 6.5, and then that's where you get the brushite forming, and then we settle that out and then recover that brushite material. One of the things that we're seeing here is that because you're doing an additional dewatering step, it suits THP facilities really well because they would be doing dewatering anyways. And then also you have centrate that has high carbon, so some facilities that are limited in carbon can use that in other locations. Second one, as most of you are more familiar with, is post-digestion phosphorus recovery, and this is Airprex, and it's more geared towards struvite recovery, where you increase the pH to between 7 and 8, and then you precipitate, you add magnesium, and you precipitate magnesium ammonium phosphate. So before I jump into some of the actual pilot work that we've been doing, and I just like to talk about what efficiencies people can expect from phosphorus recovery processes. So first thing is the phosphorus solubility. So when you look at the total phosphorus in the sludge, how much is available to recover? And so typically when you do a fermentation, just a short-term fermentation, 50% of the total phosphorus could be expected to be released back into solution. If you have a better fermentation process, 75% is pretty common. The next thing is, after fermentation, there's usually some type of thickening or dewatering step, and that is typically 80 to 85% efficient. The next one is what most people report in terms of precipitation. That's really the easiest thing. Most of the time, if you have around 150 ppm soluble P or above, you get a good 90% reduction in phosphorus there. And then in terms of particulate capture, that's the next limiting step. Depending on how complete the reaction is and how large the crystals are and what kind of equipment you use will result in how much of the actual mineral that you formed you can recover. And then when you add all those up, that's really what we see in terms of the total P capture efficiency. And one of the reasons I'm emphasizing this is because something that's kind of frustrating for us when we go and talk to utilities about phosphorus recovery is that we always report total phosphorus and most people report just the soluble phosphorus reduction. Switching over into our pilot demonstration, we've been developing this Calprex technology or trying to scale it up and commercialize since 2011. And as most of you know, commercializing a technology within this industry has some really large hurdles. And so the way we tried to overcome this and to get to scale faster, not that fast, but faster, is to work with the Water Research Foundation and to do this independent validation of our technology with many partners. So the pilot happened in Madison in 2018. We were running from April until November when it started freezing. And then our partners were Milwaukee Metro, Denver Metro, Boston Metro, and then we had our sample sent to the 3 labs, Colorado School of Mines, University of Wisconsin, and then another independent lab called Rock River Labs in Wisconsin. We've been working with engineers from mostly Wendell Kunjar from Hazen Sawyer and his team, and Leon Downing and his team at Black and Veatch. And then in terms of the fertilizer product, that is being handled by Nutrient Recovery and Upcycling with funding from the USDA. So in terms of this project, it was quite a bit of work, and there were 4 objectives. First objective was to run a 6 to 8 week pilot at 5 to 10 gallons per minute in Madison. The second one was to do a cost-benefit analysis. Third one was to quantify the benefits for the different partners. So each partner that was part of this study had really a different driver for phosphorus recovery. And so we wanted to, quantify what the benefits were based on their specific driver. And then the last one is related to reporting on the fertilizer study that we're currently conducting. I'm just going to go back a slide really quick. So in terms of phosphorus recovery during our pilot, about 20% of the total phosphorus was being recovered here, and then the rest was ending up either cycling back to the headworks because it wasn't recovered, or was entrained in the sludge and then further released in the acid digester. But the phosphorus that we had available was just what came out of the acid digester. I'm sorry this slide got a little bit cut off. So in terms of just what we were expecting from the pilot, we want our target for solubilization of phosphorus. Kind of a oh, okay. I got the time is up thing, but I have 5 more minutes. Okay, I'm almost done. So in terms of what we're expecting in solubilization of phosphorus, we were expecting about 60% because we had sampled for about 5 months in the acid digester to see kind of if we can even do the pilot there. But during the pilot, we had about 66% of the phosphorus being solubilized. And then soluble phosphorus coming out of the Calprex reactor, we were expecting anywhere between 50 and 100 milligrams per liter. Over our trial period, we had an average of 50 milligrams per liter. And then you can't really see I'm really sorry about that. I don't know what happened there. But we had about 87% of the ortho-P being reacted, 92% of the particulate, brushite and other particulate recovered in the clarifier. In terms of the ortho-P that came into our process, 65% of it was recovered. And then in terms of the total phosphorus coming from the acid digester, we were able to recover 43% of that phosphorus. Just show you a few pictures. This is a picture from Madison, the acid digesters in the background, and then we have our pilot in the foreground, our centrifuge for the acid digest, and then our chemicals and controls in a container and another skid, and then our reactor and clarifier here. And we actually produced 3 tons of brushite material during this pilot, which was later used in a fertilizer study. Brushite is a little bit different than struvite. It will never make nice pearls or anything like that. It's really a fine powder that will be granulated, and then we dry that on site. And then that material is actually growing this corn right now as we speak, and it's part of a 2-year study with Texas A&M. It's a 2-year study, 3 crops, 4 rates, and 2 different sites, so that we can have a really good comparison. And it's being compared with struvite, monoammonium phosphate, and triple superphosphate in phosphorus deficient soils. And to wrap up, all this is going to turn into my thesis, but I won't get a PhD because, and this will be published with the Water Research Foundation, hopefully by the end of the year. We're really pulling together a ton of data right now, and we can expect to see more information from this study in my future presentations. We're kind of like at a midpoint where like all the data is in, but I'm not quite yet reporting on it. And then once we get through the peer review, that'll be available to everyone. And I'm looking forward to that, and I hope you guys get a chance to see it. So thank you, and I don't know if we have time for questions. We do? Okay. Go ahead.
So with the Madison plant, you're essentially supplementing the P recovery of the existing struvite system.
Exactly, yeah.
And what would be the target total phosphorus reduction you can achieve then in the total extraction?
So I think that, you know, if you can't quite add up the amounts of the 2 systems, but we're targeting over 50% of the total phosphorus to be recovered. And whether you do 1 or 2 systems, you know, I think you can, you know, in some cases we're proposing both a Calprex and an Airprex, you know, because people need ultra low soluble P, you know, but just Calprex we're targeting somewhere above 50% of total phosphorus. Yeah. Anybody else? Okay.
Did you have any measures of the phosphorus content of the biosolids coming out?
So that was not in the scope of the study.
Number 3.
Well, we will have a number for how much was removed going into the methane digester, but we don't have a number for like what happens 30 days later, you know, within the sludge. Yeah. So, well, that was a whole other study. So, but we will have a number for like how much phosphorus was taken out before the digester, and then we can kind of model how much that reduces the precipitation potential within the digester. So, yeah. All right, thank you.
Yeah, we have